All right, AP Chem, this is your video lecture for Chapter 6, Section 1, starting a chapter on thermochemistry, so be sure to have a pen and paper ready so you can take some notes. All right, so this section is titled The Nature of Energy. You're going to talk about what energy is, how we talk about it, and how we do calculations to describe it. So energy, in a very generic sense, a lot of people don't really like this definition, but it's the definition we have. Energy is the capacity to do work or to produce heat. Both of them at the same time. The capacity to do work, and we'll define work later, or the ability to produce heat. We need to keep in mind the law of conservation of energy. It's pretty much the exact same thing as the law of conservation of mass, just talking about energy. Energy can be converted from one form to another, from light to heat, from heat to light, X-rays to gamma rays. But it can be neither created nor destroyed. So because of that fact that energy cannot be created or destroyed, the total amount of energy in the universe is constant. So if in one area or in one instance there is a decrease in energy, that means in another place or another instant there must be an increase in energy because the total energy content of the universe is constant. So you may have heard these before in physics. We have potential energy. It's the energy of an object due to position or composition. Okay, and we'll talk about that. In physics, you may have heard about energy due to position. With reference to gravitational potential energy, you hold something above the ground. It has the potential to fall. Here, in this class, in this context, we're really going to be looking at graphs. So you can think about it in terms of gravitational potential energy. That may help you. However, in this context, we're going to be using graphs using the y-axis and the x-axis, that sort of position. It'll just be a little bit easier for you. And we also have kinetic energy. Last chapter, we talked about the kinetic molecular theory for gases, the theory that says gas particles are always in motion. Here we have a similar word, kinetic energy. Okay, it's the energy of movement. It's the energy due to motion of the object, and it depends on the mass of the object and its velocity. A very massive object with a low velocity can have the same amount of kinetic energy as an object with a very small mass and a large velocity. The same amount of energy is present, it just takes less energy to move that small mass and vice versa. So when we talk about potential energy, and we refer to the energy of an object due to its position, this is what we're actually going to look at a lot more commonly in this chapter. So we have initial position and final position. Here we have initial position, and in its initial position, ball A here has a higher potential energy than ball B, and that's pretty straightforward. You should be able to figure that out from your experience in physics. And then we have the final position. After we let go of ball A and allow it to fall all the way down, that energy that was lost by ball A as it moved down, okay? One, it was some energy was lost due to friction as it rolled down the hill. And also, as it collided with ball B, that energy, that kinetic energy, was transferred into ball B. And the collision accelerated ball B enough to move it up that first little hill. So if we go back one frame, we see ball B is at the very bottom of this canyon. When ball A actually collides with it, it knocks it up one step. So we've transferred the energy from ball A into ball B, and we've increased the potential energy of ball B because we've changed the position of ball B. So energy, let's talk about heat and work here. Heat and work. Heat involves the transfer of energy between two objects due to a difference in temperature. A difference in temperature. And it's going to be very difficult for us to deal with this in any way except for differences. So like delta, okay, a change in temperature. Work is a force acting on an object over a certain distance, right? Not over a distance meaning remotely, okay, from a long distance away. it's you acting on an object with a force while you're moving it a certain distance. Okay, you're pushing a box a certain distance. The amount of work that you put in to pushing that box takes into account how far you actually did push the box. So it's force acting over a distance. Now, energy is what's called a state function. A state function. Energy is a state function. Work and heat are not state functions. And we don't want to get too caught up in that definition, state function. It sounds like it's going to be a big deal. But state function, it simply means state function refers to a property of a system that depends only on its present state. A state function or a state property does not depend in any way on the system's past or future states, just on what it is right now. So the energy of a system is a state function. It has only to do with what it is doing right now. Work and heat are not state functions. They do depend on the past state or the future state of the system. Hopefully that'll come a little bit clearer as we do some practice problems with this content. Now, let's change this into a little bit more chemistry-based as opposed to physics-based. Talk about chemical energy. We have two ideas we want to get across really, really solidly when I have these firmly in hand. We have a system and we have its surroundings. So a system is the thing that we're looking at. The system is the thing that we're looking at, and the surroundings is everything else. Okay, everything else. So a system, part of the universe on which we wish to focus our attention, and the surroundings include everything else in the universe, everything else. And to get a better idea, be sure to look at the diagrams on pages 244 and 245 in your textbook. These diagrams, pretty simply depict the difference between surroundings and systems. Especially when we get into exothermic and endothermic reactions, make sure you have that firmly in mind. So, endothermic, exothermic reactions. Okay, so an endothermic reaction, heat is going to flow into the system. Okay, an endothermic reaction absorbs energy from its surroundings. It's a reaction that requires energy to continue, to move to completion. It needs to absorb energy, and so what it's doing is it's absorbing heat from the surroundings, and the heat is moving into the system. And the opposite of that is the exothermic reaction. Energy is going to flow out of the system and into the surroundings. So there's a release of energy, because that energy is going from the system to the surroundings. Now, any energy gained by the surroundings must be equal to the energy lost by the system. Okay, that is a hard and fast rule based on the law of conservation of energy. So anytime we see an increase in heat in the surroundings, there must be an equal decrease in heat in the system, and vice versa, at all times. That law can never be broken. All right. Let's see how we're doing with some of these definitions. I want you to answer this question and be able to defend your answer. Is the freezing of water moving from the liquid state to the solid state an endothermic reaction or an exothermic reaction? So think about what's happening there and whether or not energy is going or heat is going into the system or into the surroundings. The freezing of water is actually an exothermic reaction because we have liquid water, and keep in mind the liquid phase of water is higher energy than the solid state of water, right? In layman's terms, ice is colder than water, the liquid water. And so in order to get from that state of liquid to solid, you have to become lower in energy. You have to get rid of energy. So you have to take energy from the system, the water, and remove it. You have to release energy into the surroundings. And by definition, that makes it an exothermic reaction. All right, here's a couple for you to practice again. I want you to classify each of these processes I have listed here as exothermic and endothermic. And I want you to, again, be able to justify your answer. Just to help you, the system, okay, the thing that is defined as the system is underlined here in each example. So go ahead and press pause, come up with an answer, and I'll go through all of them in a moment. All right, A, exothermic. Your hand is the system. Your hand is what we're paying attention to. Your hand gets cold when you touch ice. Okay, which one's higher energy, your hand or the ice? In other words, which one's hotter? Your hand. All right. Now your hand goes from a state of being warm to being cold. So your hand is losing heat. Heat is going from your hand into the ice, and we've defined your hand as the system here. So the movement of energy from the system into the surroundings makes this an exothermic reaction. B, the ice. Okay, the ice gets warmer when you touch it. Now this is the reverse of A. Okay, this is the exact opposite of A. So whereas A, we're paying attention to your hand, we're defining your hand as the system. Here, we're talking about the ice as the system, and your hand is the surrounding. So the ice is getting warmer. The ice is absorbing energy. Energy is moving into the ice. It is moving into the system. That makes it an endothermic reaction. C is endothermic. Water boils in a kettle of being heated on a stove. So what's the system? The water is the system. And what are you doing to the water? It's on a stove. It's being heated. You're using combustion, a flame, to move heat into the system, endothermic. D, water vapor condenses on a cold pipe. Water vapor condenses on a cold pipe. So, water vapor is the system. Water vapor is the system. So, we have water vapor, which is the gas phase. Okay, through the process of condensation, it moves from the gas phase to the liquid phase. There has to be a decrease in energy there. Okay, there has to be a decrease in energy to get to the highly energetic gas phase and to the not as energetic liquid phase. And where's that energy going? It's going from the gas into that cold pipe. The energy is moving from the water vapor, high energy, to the low energy cold pipe. So it's going out of the system, the system. It's leaving the system. So that's exothermic reaction. E, ice cream melts. Okay, ice cream melts. Again, ice cream is in that solid state. Okay, that very low energy solid state. It's very cold. It's melting. It's heating up. Heat is moving into the system and moving the ice cream from the solid phase to the liquid phase. So heat is going into the system. All right, here's another one. Instead of just defining exothermic or endothermic here, I want you to define the system and the surroundings in each of these situations. And I want you to denote which way the energy is going. So I want you to identify the system, and I want you to identify the surroundings in A and B. And then I want you to indicate, is the energy going from the system to the surroundings, or is the energy going from the surroundings to the system? Go ahead and press pause right now so you can have an opportunity to do that. All right, A, methane is burning in a Bunsen burner in a laboratory. Okay, methane is burning in a Bunsen burner in a laboratory. So here, methane is going to be the system, the laboratory is going to be the surroundings, and methane is burning, it's releasing heat from the methane. The methane is the fuel. So this is going to be an exothermic reaction. Okay, the laboratory around the Bunsen burner is going to warm up. It's going to heat up. So that's an exothermic reaction. Energy is going from the methane into the surroundings, into the laboratory. All right. B, water drops sitting on your skin after swimming evaporate. Okay. Now, you can actually choose either one. Okay, the water drops can be the system, and your skin can be the surroundings, or just as easily, your skin can be the system and the water drops can be the surroundings. It simply depends on where you want your attention to be, what your focus is. And either one is completely okay. You simply need to realize that the water drop is evaporating, so the water drop is going to be absorbing the heat from your skin. Okay, so if you identified your skin as the system and the water drop as the surrounding, that is going to be an exothermic reaction. Okay, heat is moving from your skin into the water drop. It's an exothermic reaction. Now, if you identify the water drop as the system and your skin as the surroundings, if you wanted to look at it from that point of view, energy is still moving from your skin to the water drop, but because of the change in attention, this actually becomes an endothermic reaction. Energy is still moving the same way, it's just we're going to describe this as an endothermic reaction because we're paying attention to the water drops. We've defined the water drops as the system, and energy is now going into the system because we've changed what we define the system as. So for B, either one works. You just need to make sure that you can justify your answer and that you did in fact indicate that energy is going from your skin to the water drops. All right, here's another thing to practice with. Hydrogen gas and oxygen gas react violently to form water. Okay, and if you guys have seen The Martian, can you see that Matt Damon in the movie rendition of this tries to do this in order to make water, and he underestimates the presence of oxygen and gets a pretty darn big explosion. So we have hydrogen gas, oxygen gas reacting violently to form water. I want you to answer this question. Which is lower in energy? Which is lower in energy? A mixture of hydrogen and oxygen gas or the water? Okay? Is the hydrogen gas and oxygen gas higher energy or lower energy than the water? Okay, and be able to explain this. Go ahead and pause the video until you can come up with a response and be able to justify it. All right, it's going to be the water. The water is going to be lower energy. And the way you can tell is because there was a release of energy. There was a release of energy, just like, way back when, earlier in this presentation, we had ball A being held at a high position, and it was let go. It was allowed to fall. Okay, that was, the quote-unquote violent reaction here. And where did it settle? At the bottom, at the lowest energy possibility there, because there was a release of energy. Same thing here. The hydrogen and oxygen gas have a lot of energy in them, a lot of potential energy. And through their reaction, that energy is released, just like that potential energy in ball A was released as it fell. That chemical energy in the hydrogen gas and oxygen gas is released as they react, and that's that kind of explosion, that violent reaction. That is the energy being released. So if there is a release in energy, your products are going to be the lower energy version, the lower energy portion of the reaction, because there's less energy in your system. Okay, the energy has been released into the surroundings. All right, so this entire chapter is titled Thermochemistry, or also known as Thermodynamics. Thermodynamics is the study of energy and its interconversions. Okay, interconversions mean just being changed from one form of energy to another. And we're going to do a lab for this chapter. I know we haven't been doing this very long, but we are going to do a lab where we're going to try to quantify an interconversion of energy. And remember the law of, not remember, but I hope you remember from physics that the law of conservation of energy is often referred to as the first law of thermodynamics. Okay, and this is pointed out in your book on page 244. It's actually their definition of thermodynamics. The study of energy and its interconversions is called thermodynamics. All right, so that was, then we're going to talk about internal energy, and we're going to represent internal energy as a capital E. So the internal energy, or E, of a system is the sum of the kinetic and potential energies of all of the particles in the system. So whatever you define the system as, if you add together all the kinetic and all of the potential energies of everything in that system, that is your internal energy. That's your E. Now, it's not really possible to calculate E. Okay, it's simply not feasible for us to do here. But what is a little bit easier for us to do is calculate a change in E. So we're going to see delta E a lot more commonly than we will simply see a capital E. So to change the internal energy of a system, we're going to have to do some amount of work, and we have to see some amount of heat. So a change in energy is equal to Q plus W, where Q represents heat and W represents work. So we have heat and work. We're going to be doing some work with these, no pun intended, with these equations here. So try to keep those terms straight. And so that was a lot of information in a very small amount of time. If you want to pause this video, go back, watch it again. Make sure you take notes on that. I'm going to try to represent those in PowerPoint form here in a moment, but that's going to be something you're going to want to pay attention to. I know it's pretty succinct. Don't be afraid to watch it more than once. So, internal energy continued. Thermodynamic quantities consist of two parts. Okay, the quantity. Okay, we're representing the information here. We're representing that energy. We need two parts here. We need a number. Okay, and that number represents the magnitude of the change. And how much did it change? And we also need a sign that indicates the direction of the flow. Okay, is the flow going into the system or out of the system? So we need to know how much energy is moving, and the sign indicates which way it is moving. Now, the sign, when you're picking a negative number or a positive number denoting the movement of energy, you always need to be operating from the point of view of the system. So for an endothermic process, Q is going to be positive. Okay, Q is going to be positive. The heat is going to be positive because energy is going into the system. Okay, into the system. Over here on this diagram, we have at the bottom right the setup on the right where energy is going into the system. That's an endothermic reaction right there. Endothermic because energy is going into the system. Notice that the change in E is greater than 0. Okay, the change in internal energy is greater than 0. It's positive, and so energy is being added to the system. The opposite of that is an exothermic reaction, which energy is leaving the system. So the change in energy, there's a certain amount of energy leaving. Okay, and so we need to denote that with a negative sign. So the change in E on an exothermic process is going to be less than 0. It's going to be negative. Now, we have a similar set of rules that has to do with work. Okay, it has to do with work. Still talking about internal energy. The sign, okay, you have magnitude and the sign. The sign is still going to be from the system's point of view. Always the system's point of view. If the system does work on the surroundings, W, work, is going to be negative. Okay, it's going to be negative. If work is done on the surroundings, if energy is used to do something to the surroundings, work is negative because it's from the point of view of the system. If the surroundings do work on the system, okay, so the surroundings are expending energy onto the system, W is going to be positive. The amount of work is going to be positive because the system is receiving work. Okay, work is going into the system, so it's going to be positive. Talk about work a little bit more. Work as an equation is going to be represented by pressure times area times change in height. In this example I have over here with the pistons, where P is pressure, A is area, and delta H, change in height, is the piston moving a certain distance. Now, you can simplify that equation to yield P times delta V. Okay, so it's going to be pressure times the change in volume. You can simplify that a little bit. And P times delta V is going to be a little bit more useful for us when we get into real life situations. Not only because it has a three-dimensional application, but it simply has fewer terms to worry about. And notice that from the change in height, okay, and the area upon which the pressure, the force is being applied, which is pressure, you can extrapolate the change in volume. Okay, so they are directly related. It's just that P times delta V is a little bit easier to use when we do our calculations. All right, still talking about work here. If we talk about the situation, an expanding gas, okay, that change in volume is a positive quantity. Okay, the change is positive; it's getting bigger. Okay, so the change in volume is bigger. The volume is increasing. It's going to be positive. So, therefore, the change in volume and work must have opposite signs. Okay, opposite signs. If the volume is going to increase, that means that work is going to be done on the surroundings. So we're going to use this equation a little bit simplified. Work is equal to negative P delta V. Okay, W is equal to negative P delta V. And if you remember, we have a whole bunch of different constants so far. And if you ever need to convert between liters times atmospheres and joules, the statement of equality to use for your conversion factor is 1 liter atmosphere is equal to 101.3 joules. So that's the statement of equality for your conversion factors. All right. So using the equation that we just went over, which of the following performs more work? Is it A or B? So go ahead and press pause so you can do some kind of simple calculations here, and tell me which one performs more work. All right, it turns out that they actually perform the same amount of work. We have 2 atmospheres and a change of 3 liters. 2 times 3 is 6. And in situation B, we have a pressure of 3 atmospheres and a change of 2 liters. 3 times 2 is also 6. They're both 6. So the amount of work done is the same. All right. One more. For each of these systems, I want you to determine the sign of delta E for each of the following. So just the sign. Give me positive or negative. Okay. So for A, an endothermic process that performs work. Okay. When work is greater than heat, is that going to be a positive or negative delta E? When work is less than heat, is that going to be a positive or negative delta E? And do that for both A and B. For the first situation, the endothermic process is an endothermic process when work is greater than the amount of heat. When work is greater than the amount of heat, delta E is going to be negative. Delta E is going to be negative. But when work is less than heat, delta E is going to be positive. Delta E is going to be positive. For B, work is done on a gas and a process is exothermic. Delta E, when work is greater than heat, delta E is going to be positive. Delta E is going to be positive. But on an exothermic reaction or exothermic process, when work is less than heat, delta E is going to be negative. And I'd like to point out, if you look at A and B, they're kind of opposites here. For the situation in which work is greater than heat, if it's an endothermic process, delta E is negative. But for an exothermic process, delta E is positive. So we want to remember that kind of dichotomy. When work is less than heat on an endothermic process, delta E is positive, but for an exothermic process, it's negative. So there's that kind of dichotomy there. All right, so that's the end of section 1, the nature of energy. Be sure to attempt those end of chapter problems, and if you have any questions on them, be sure to bring them to class because we will be working on them in class. All right, I'll see you next period.